Thank you. Thank you very much for the introduction and for the invitation. It's a pleasure to be here. So this is joint work with Christina, myself, Mike Todd, and Ian Melbourne. Okay, so I'm going to start by considering a system that I'm going to denote by T. And on this system, I'm assuming that I have an invariant measure that I'll call mu. And the point is, I'll introduce also an observable function here, V, that takes values in Rd. And we want to study the sums that I'll denote by Vn of these observable functions. Okay, so take the ergodic sums, and we want to prove some sort of limit theorems for this. Of course, if you are in the central limit theorem regime, then you expect this to converge to some, let's say, random variable z with a Gaussian distribution. And I'm assuming here that just for fun, that V has a zero integral here. And of course, there are lots of results about this with lots of people in the room doing this. And one can enhance this by trying to prove a weak invariance principle. So if I just define Sn of t to be 1 over square root of n, and then I put here sum of V, okay, then one might expect that this would converge to Brownian motion. Also, if you have a regime where central limit theorem holds, okay? So basically, for this, you need some sort of regularity of your system and of your observable, and typically there's a T, right? Thank you. Sorry? Convergence in law, yes. Sorry? Ah, yes. Thank you. With respect to the measure mu. Okay, so you can hope that this thing here holds if you have a nice system and a nice observable, okay? So by nice observable, I mean something that is square integrable, and by nice system, I mean something that has sufficiently fast decay of correlations, okay? But for the purpose of this talk, I'll abandon this nice system, okay? And the point is to work when either the observable is not square integrable, and then we have a heavy-tailed distribution, or when the dynamics is very slow, and then that might create also some sort of lack of mixing, which ultimately leads you to a convergence to a stable law where this doesn't simply apply, okay? So in this kind of situation where you have either a bad observable or a bad system, then what you try to obtain is to find some normalizing sequences Bn such that your Vn gets stabilized and goes to, in law again, to an alpha stable law, okay? Right, so there are several results about this. Comes to mind the paper of Guzel, but also there's a lot of work on this by Melbourne, Zweimüller, François Penn, Hongkong Zhang, Jung. Well, a lot of people proved this kind of limit. And in fact, there's instead of looking at this type of convergence, they can look at this functional type of convergence, and instead of getting a stable law there, then what they get is a Lévy process, okay? So basically, now, again, we have the same processes here, okay? So the difference is that now the normalizing sequence is some Bn, okay? I'll tell you a little bit later what does Bn look like. And basically, what you have is that this thing here converges in law to an alpha stable Lévy process. So the main difference here is that while the Brownian motion has continuous paths, here the Lévy process has jumps, okay? So instead of working in the C01, I'll be working the space of càdlàg functions defined on 0, 1. And by càdlàg, I mean something, then continuous part, and at some point there's a jump, and it's like this. So you have here you have limits both on the left and on the right, and here it's continuous on the right. Okay? So that's sort of types of things that we expect in the limit. Okay, so let me give you some examples of what we'll be working on that somehow will motivate our main theorem, okay? Which I'll state only in the end. Okay, so let me give you. So I'll start with a very simple system. So I'll take this time a regular dynamics. So I'll take just 2x mod 1. Okay, so this is as perfect as one can get. And but for the observable, I'll choose a bad observable in the sense that this number can be any number as long as it's not a rational number, and like that. Okay, so basically, so your system is uniformly expanding. And there is 5/4 here, and the point is that the observable here has a vertical asymptote, okay, and it's heavy-tailed, okay? And that's the problem, because whenever the orbit gets near this point, this means you get a huge contribution from this observable, okay? And it's so large that even when normalized by this Bn, it produces this jump that you see here. Okay? So if you're looking, for example, I'm going to try now something which is try to look at how does this Sn of t looks like. Okay, so you see that Sn of t is this is a sort of path piecewise constant function, right? And it jumps at every j divided by n. Okay, so let's say your orbit is around here for the moment. Okay, and so basically, let me try using now the colors here now. So basically, your Sn is doing some things like this, small fluctuations. Okay, so this I'm already assuming that n is large, so that this is the size more or less 1 over n. Okay, and then so you have some fluctuations here, and then at some point you go near this point here, and this causes a big jump. And because this is positive, it's going to jump high. Okay, so you get a big jump here, and then you do some sort of fluctuations here, so that in the limit, what you see is a Lévy process like that. So there's something here, there's a big jump. And that's how it looks like, okay? So in order to prove convergence, you have to use some metric in D, okay? And the first one that people used was the J1 metric, okay? So the J1 metric simply tells you that, so there's a metric in D, so let's say 2, this is the infimum over the lambda, and then you take here the maximum of U1 composed with lambda. So this is infinity norm, and here is the identity map minus lambda, infinity norm as well, and lambda is non-decreasing, continuous time reparameterization. Okay. Take the infimum over all these possible. So the idea is that, right, one would like to try to use the sup norm, like for the continuous paths, right? But you can't because you have these jumps here. And so what you do is you kind of allow some time reparameterization that allows you to make this orange path close to the white one, okay? And so this is the famous J1 metric in D01, okay? Right, okay. So this is one sort of example. So here, it's fairly easy to prove that, in fact, you have this convergence to an alpha-stable Lévy process, okay? So let me get here some more interesting stuff that we are trying actually to capture with this new result. So let me go to this new example, which appears in some notes published on Kuzel's webpage, okay, where he considers the same system, so it's the same system, to X mod 1, but this time, the observable function is maximized at 0. Okay? So now the problem is when you come near 0. Right. And why is this a little bit different? Is that now 0 is a fixed point. Okay? That means that when you go here, you still linger here for some time. Of course, you are exponentially fast moving away, but because it's fixed, you still do some iterations there. Okay? So this means that if I now try to make this picture again, let's say I'm wandering around this part here first. So in this, there is sort of small kind of fluctuations here. Then I go near 0. And when I go near 0, I know that my observable function now will make me jump. So I'll jump, let's say, here. Big jump, okay? But now, since I'm on the vicinity of a fixed point, I'm moving away with, next time, I'll move 2 times in that direction, but I'll still have a large observation. So I'm going to jump again, not so high, in fact, around 1/2, the minus alpha, something like that. And then there is a smaller jump in the kind of a geometric kind of way. I stabilize here, and then I get another sort of fluctuations here. Okay, and so, but in the limit, what one observes for the process is that basically you've got something like this, and then you have a big jump up there, and that's it, because these little intermediate jumps, they get squashed into the same time point. Okay? So, right. How can one prove this sort of limit? So now you see that J1, the J1 metric is really not good for this. Okay? It's not good for this because you just can, in here, you have to think that you'd like to make a time shift, and you can make the orange and the white path to get aligned. But here, you can't get images from the white path close to these steps that you went through. And so the J1 metric does not allow you to get a convergence result here. So the trick is to use the M1 metric. Okay, so here you use the M1 metric. So again, a Skorohod metric. Okay, and the difference is, I'm not going to the details how you write the definition, but basically, instead of having some match between U1 and U2, what you do is you look at the completed graph. Let me call it gamma U1 and gamma U2. And then you ask for just a matching of the completed graph, more or less in this sense. Okay? So basically now what you do is you get, so I can do this thing. So basically, I just look at the completed graph, okay? And so it means that I look at things like that. Okay, and for the white one, maybe I can draw with another color. I look at this. Okay, and now if you imagine then, okay, with the time parameterization now, I think one can convince oneself that if you go this way and if you go this way, if you allow for some time reparameterization here, you can match this blue line with this blue-orange line with this white and green line, okay? Right, so if you change the metric, you still can get convergence here. That's the point. But as you can see, now in the limit, you lost a lot of information because you lost this excursion here. You don't get this information anymore. That's what we are trying to recover with our results here in the end. Okay, so basically, so there's an excursion here. So let me draw what one would like. One would like that we'd have something like that. Then we'd have a jump here in a kind of a geometric type of way. Okay, so I want to capture this sort of excursion, okay? But also at the same time to have a notion of, okay, so you know that this thing is all collapsed in this time point here, but I want to know what I visit first, because, so here you know I'm going up, but I could have gone up, down, whatever, okay? So I want to keep that information as well. So that's what I've got to call here the decoration for my Lévy process, okay? And so in our final theorem, I'll have, besides knowing these points, I'll have precisely what do you call an excursion that's telling me how did I get there, okay? Right. So it's this stuff we want to capture, that when you just look at the limit, even though you can prove that there's a limit here for an alpha stable Lévy process, you lost your information during the jump. Okay, so this was the case where you had good dynamics, bad observable. So let me get to the situation where you have a good observable, bad dynamics, okay? So here, let me well, cite some people here. So there's, of course, Guzel, again. There's Titan Kaminska. And also Melbourne and Weimüller. Okay, so what they consider is the LSV map. Okay, so the map with intermittency. And put here the formula x1 plus 2 to the power 1 over alpha, x to the power 1 over alpha, and here 2x mod minus 1. And V, I'm just going to say it's in L infinity, and it will have 0 average, okay? And for the purpose of the drawings, I'll assume that V at 0 is strictly larger than 0, okay? So here the map looks like this. So it's basically that one, except that, well, this part is actually the same. This one has here a tangency, goes like that. Okay. So now the problem is the following. The problem is with the map, not with the observable, because if you are away from 0, then everything is nice. Okay, so you sum and you have sort of this small type of fluctuations here. But then there is a problem when you go here near 0. Because of the tangency, the orbits get kind of squashed over here, okay? So there's a sticky point that makes you wander there for a long, long time, which means that during these periods, your fluctuations are going to be small, but every time in the same direction, because you're kind of repeating the same observation over and over for a long, long time. Okay? So basically, if I try to draw now, again, this fluctuation kind of thing, so in here, what one would see is something like this. So you have this, while you're around here, you have these small fluctuations, up and down, and so on. And then you get near this point, okay? And what's going to happen is that, okay, so you're going to have small fluctuations again, but you're going to have these small fluctuations for a long, long, long period of time, and you're always going up until you get here, and now you are sufficiently away, and you get these type of small fluctuations. So now, what you'll see is that you get something like that here. There's a big jump here. And again, you get a convergence to an alpha stable Lévy process. Okay? Of course, here you can't use the J1 metric. Okay, that's one of the results that Titan Kaminska shows, is that the J1 metric, this doesn't work. But as Roland and Ian showed, if you use the M1 metric, then you still get convergence here. Okay? But again, you see that in the limit only gives me this white picture. You lost whatever was going on over here. So what we're trying to get now is, again, this profile of what was happening during this collapse of time into this jump. Okay? So hopefully we want to recover something that will do this and that, because basically the jumps are so small that in the limit they get like a sort of continuous thing like that. So, no, like that. The process kind of stuff. So And then, of course, if I try to open up to understand what's going on here, then the profile here should be something that does more or less like this. Okay, so that's what we're trying to see in our limit theorem. Okay, so we have the Lévy process, but we want to put a decoration, and the decoration should look like that. Okay, right. So let me go over for the fourth type of example. So this fourth type of example comes from maybe. Okay, comes from a paper with Christina and Mike. And we just took, again, a simple system, 3x mod 1. And but now the observable is a bad observable. Okay, so let me draw here the map. If I can make more or less drawing here. So the issue with 1/8 and 3/8 is that this is a periodic orbit. Okay, so of period 2, 1/8 go to 3/8 and comes back. Right. So this would be something more or less. It should be some sort of angle here, something like that. Like 1/8, 3/8, and then it comes back. Okay, and the observable now here looks like this. So we have very high values when I go near 1/8. Okay, and then on 3/8 it goes like this. Right. So these are heavy-tailed, pretty much as it was in the first situation here. Where is it? Ah, here. Yeah, in this case. Okay. So if I try now to draw the orange and the white picture, it should look like this. So you have small fluctuations here while you're wandering around here, let's say. And then you go near one of them. Okay, either 1/8 or 3/8. So let's say I'm going first near 1/8. Okay, so if I go near 1/8, then I'll have a big jump. Okay, but then since I'm once I get near 1/8, I'll get afterwards near 3/8. I'll also get a big jump, but this time down. So it will go down, but not as much as I went up. Okay, so it will go down. But if I am here, I'll have to be back there. So I'm going to jump again up, but not as much as I jump down. So I'm sort of getting some sort of geometric kind of law again, and a sort of stabilizing way, so that in the end, then I'll get into the normal type of fluctuations again. And in the limit, well, in the limit, what I'll see here is again just a big jump. Okay. So that's what I'll see in the limit. So this will still have convergence. Well, I'll have to talk a little bit about other spaces, because this time, well, you don't have convergence in J1 metric. You don't have convergence in the M1 metric, okay? And even if you get to the M2 metric, which is even more general, so for the M2 metric, what you do is you complete the graph and take the Hausdorff distance between the two, okay? So this is even more general because it allows you to go back and forth, so you don't have to go in the same direction that the two are going, so it's even more general. But even in the M2 metric, this is going to fail because you've got overshooting here because you go much higher than what the limit sees. Okay, so you can't approach this by something that looks like, I'll draw it in green, I guess. You can't get a matching between the completed orange one and the green one, okay? Because of this thing here. You can't. Okay, so you have a problem here with convergence, which can be solved by going into a Whitt type of space. Let me call it E, that I'll describe after this, okay? And so, but you can, well, you can still recover convergence here, right? But our aim is again to capture more than that. We want to capture whatever was going on here. So I want to see some sort of excursion here that looks like this. So you have, let me draw, I've been drawing it in green. So let's say there's some green stuff here. And then I'll go up, I'll go down, I'll go up, I'll go down, I'll go up, and then I'll stabilize here. Okay. But as you can see now, it's more complicated than in the first case where I just went it up. Okay, so I want a certain, also to have a certain profile here that is tells me exactly how did I get here. Okay, so in this case, I got here with a sort of oscillating way. And I want to see that in my profiles. Okay, so our theorem is just, we are going to have convergence to a Lévy process like this, and we are going to put in decorations so that everything is in the limit. Okay, so you don't lose any information. That's the point. Okay, so I'm already a bit late. So let me go this over this just very fast, just to say that there's a sort of situation similar to the third one for billiard maps. Okay. I'm not going to describe these billiard maps. I assume that you've somehow learned about them with cusps. Okay, and so the point is that you have got, let's say you have a map table, and then there is some corner, and you've got a cusp here. Okay, so the point is that when your orbit goes inside here, then pretty much as it happened with the sticky point, you kind of get squashed over there, and you get, at some point you get out, but you lose a lot of time there, okay? And so, well, here I have also to mention that there are lots of results about this. So by Jung and Zhang, okay, then Jung, Zhang, and François Ben. And there's also this paper of Melbourne and Varandas. And then there's a joint paper with all these authors. Okay, so so I won't go now into more drawings, just to say that in here, some other profiles can appear. So for example, there can be something like, goes like this, okay, where you go like that. Okay, that's one way. Or you can have more sophisticated stuff, like for example, you can go up, down, and then up, for example. And there can also be overshooting, for example. You can have something like that. Then it goes like this. Okay, but in this kind, so there will be these sort of profiles here that are, while these are discrete, these are more continuous nature, okay? And the point is we are trying to capture everything in the same theorem. Right, okay. So that takes me to So as you've seen, the Skorohod's metric are not enough. So J1 only serves for the first example, fails in all the other ones. M1 could be used in this one, in that one, but not in this one. It could be used here, not here. This would be good in M2, for example, but this one and that one fail in M2. Okay, so you need to have more structure here. Okay, so let me introduce now the E space from Whitt. Okay, so Whitt spaces. So the point now is that I want to capture more information, okay? So what I do is, instead of taking D01, the càdlàg space, I'm going to take this enriched space where I have a trio here. So I have U, I have S, and then I have here the excursions. Well, not excursions. Okay, so the first one is just something in D01, okay? So a path in D01, okay? So the second, so S will contain the discontinuities of U, okay? So S contains the discontinuities of U. And the fourth one, so for each, let's say, tau in S, okay, yeah. Sorry? Yes. Mm-hmm. Yes. Contains. Yeah. Yes. No problem. Okay, so so K tau is what? Is a compact connected subset of RD containing U of tau minus and U of tau. Okay? So it basically looks like this. So you think about the Lévy process, right? And you've got jumps. Right. So now there are some, at some points, so this may not be necessarily a discontinuity point, and I can put there something, okay, some decoration. But in here, for example, since I jumped, here my decoration has to include these 2 points, okay? So that's the rule. So it might be like that, for example, just a little bit might coincide here. There might be some other points like that, yeah. Yeah, the observables can be d-dimensional, although all my examples are one-dimensional, just because I can't draw d-dimensional. Okay, but the theory is it can be done in other dimensions. Okay, right. So so you need a conversion, so a metric here. Unfortunately, it's not difficult to get one. So you just use the idea of the M2 metric, okay? And for, let's say, 2 elements of E, you just find the Hausdorff distance between the completed graphs of U1 and U2, okay? With the decorations inside, okay? So this all, everything is in this completed graph. Okay, and then you take the Hausdorff distance. Right. With this metric, E is separable, not complete, but separable. There's some way of making the metric complete, but then it's not separable, okay? But here, let's stick with the version that is separable, not complete. And okay, and this is already good because with this E space, I can already get conversions in all these situations, which is nice, okay? But still, because this is not fine enough, right? This only puts you a set here. It doesn't tell you exactly what's going on over there. So you need some more information, okay? So that's why with Mike and Anextina, we introduced this F prime space. So let me say that Whitt always also has an F space where he is going to get more information of what's going on this third component here. But for example, you would not be able to distinguish a case like that, for example, like this one, because it wouldn't keep the information of the intermediate jumps. Okay, so that's why we introduced the F prime space, because we just made Whitt space a little bit better. Call it F prime. And sorry, before I get to F prime, before I get to F prime, I need to introduce here d tilde. Okay, sorry, let me introduce here d tilde of 0, 1. So this is just d01 quotient by this relation where u1 is the same as u2 if and only if there is a time reparameterization that can match the two, where the time reparameterization is non-decreasing, continuous, but, and here's the big important but, it does not need to be necessarily close to identity, okay? It can be any time reparameterization, actually. Okay, and so in this space, we put a sort of metric coming from the sort of similar to the J1 metric. And we simply say that we take the infimum over all the reparameterizations and take U1 composed with lambda minus U2 and take. Okay, so that's the space we want to where we want this third component to live in, okay? So in F prime, we have, so it's again a triple. This time I'll put here E tau. So this E for excursion. Okay. Okay, so the first ones are as before. Okay. U is in D01. S is contains the discontinuities of U. And then E tau lives in D tilde. Right? And what you want is, you want that E tau of 0, so this excursion starts at U tau minus, and it will end precisely at U tau. Okay? That's what you want from F prime, right? And, okay, so that in order to establish convergence, so you have to put a metric here again. And the metric is simply obtained by projecting into E and projecting to D prime. Okay, so let me try to explain this a little bit better. So basically, for a U in F prime, you just do the following. You project it into E by making it EU S, and then here I put K tau, and K tau is just the span of the range of the E tau. Okay? So this is a simple thing. And the more trickier part is to project this into d tilde. So how does it work? Okay, so let's say you have a picture like that, right? But for every one of these vertical lines, you have an excursion, right? So what you do is we open up time so that during this, so I was supposed to see something like that, and it should be something here. So I open up time here so that in the middle, I can put whatever the excursion does, okay? So the excursion can go, for example, go up, go down, go here again, and then at some point settle there, okay? So we just open up time and put whatever the excursion does. So the excursion can also, for example, at this stage, so there'll be this big jump here, can be one of these sort of continuous type kind of things, okay? And well, it can't be like that because if it's, well, this only has to contain, but let's say I'll do something like that. Okay? And then what we get is we get an element of d tilde, okay? And the point is, so you see in d tilde, we allow for time reparameterization. So opening the gaps is not problematic at all. And then we ask that the metric simply gets the, so there's the distance in f prime between some u1 and u2. You just get the maximum of the distance in E between the projection maximum of this plus, now you get a distance in d tilde of these projections there. Okay, so that's how the metric looks like. And with this metric, you can prove all these convergence results and also hopefully get the information in this. So these things will be this kind of green stuff that I'm putting here on the right. Okay? Right. Okay, so let me skip this part, otherwise I can state the theorem. So let me try now fast. No, yeah. Sorry. Yeah. Okay. Thank you. Sorry. By the way, that metric is separable, not complete. But if I use the complete metric, which is not separable in E, then I'll get the same property in F prime. Okay? Okay, so let me see if I can do this fast. Okay, so what we use in our theorem, so you're going to use inducing, okay? So the idea is that we are going to induce outside of the problematic region where that causes the jumps. Okay, so here you're going to induce outside this point. In Guzel's example, we induce outside the fixed point, and in here we'll induce on the right branch. Okay, and the idea is that during the let's say the inducing period, you should it's the inducing period that will going to get us the excursions. Okay, right. So let's say we have a set X sitting on M. Okay, well, I'm assuming that mu of X is positive measure. And then, of course, I'm going to define here a return time function here. So I'm going to take R of X to be the minimum J's such that Tj of X is in X. Okay, and then I define just the induced map Fr, F to be Tr, okay, which does this. Right, and then I define the capital V to be just Vr, okay, and define the processes. Okay, so this is for the original dynamics. That's the one I want a result for. And then I use here the induced process, which has the same normalizing constants, okay? But instead of V here, I'll use the induced thing. Right. Okay, so what are the hypotheses? Okay. Well, the first one, and really important one, is that, well, I have, so I'm going to assume, so the point is I want to get a result for this one, and I'm going to assume I've got a result for this one. Well, because typically for this system, since we are going to induce, typically the induced system is well behaved, okay? Is uniformly hyperbolic. And so I'm going to assume that W and V is converging in law with respect to mu x, okay, to some alpha stable Lévy process, let me call it L alpha, okay, which has a spectral measure with a spectral measure that looks like this. There's some in this set here, and it's some AIs, delta, WIs. Okay? So for example, the spectral measure, let's find a complicated case. It's not, no, it's, did I erase it? Yeah, I erased it. The one that goes up and down, okay? So the WIs will just have 1 and minus 1. Try to get the fact that sometimes I go up, sometimes I go down, okay? But if you're in RD, then this could, and if you're, let's say, in a billiard, this can be like a sort of direction. So this leaves, WI lives in SD minus 1, okay? But, yeah, I should have said something more about this, but let me get to the result, and then in the end, if you have questions about that, you can ask. Okay, so that's the first assumption. So I'm going to assume that I've got convergence, and this convergence is actually in J1. Okay, I can do now this in J1 because in J1 I don't see whatever is happening in the excursion. So there's no problem in assuming that. And then the second condition is a condition that is going to enforce some sort of matching between a link between the limit profiles and the dynamics. Okay, so I'm going to require that 1 over Bn maximum with j between 0 and n of the distance of d tilde between xi and zeta. I'll have to say what is xi and zeta, composed with fj goes in mu x goes to 0. Okay, so now how does this look like? So xi of t is just v tr. Okay, so this is going to give me what? So this is going to give me whatever the inducing excursion is doing. Okay, so let's say if you're taking the LSV map, for example, then what it's going to get is exactly those sort of orange things in the middle, right? Okay, and now what I have to do is I have to advance with some profile, okay, which must be given. So it's the profile I'm going to put as decoration for my alpha stable Lévy process, and so the zeta. So no, this is going to have a strange formula, but anyway, is basically performing whatever the profile is telling you to do. Okay, b minus v v1. Okay, and this is an annoying thing that we would like to get rid of. There is a sort of projection. So you have to somehow to choose which profile you want to put. Okay, so in these situations, there is only one profile, right? But you can have several cusps, several intermittent points, and then you want to associate the right profile, okay? And so this function pi is basically doing that. Okay, so let me not say anything else, otherwise I can't state the theorem. And the theorem, I can't afford now to spend more time cleaning. I'm going to state here, tells you the following. So if the hypotheses are true, then what you have is convergence of Wn as it must be looked so I know that this in here it's defined in D, but you can project D into F prime, okay, where you have trivial excursions, and then the limit with is computed with respect to mu, not mu x, is going to be some L alpha, F prime. Okay, so this lives again in F prime. So this is a statement in F prime. Okay, and the limit looks like this. So you've got so L alpha of F prime is going to be L alpha. Then it's going to have here something that contains the discontinuities of L alpha, and here it's going to contain the excursions. Right. Okay. So L alpha is just what? L alpha is just, you have to normalize this because you use the induced time, so you have to normalize this by the average inducing time. Okay, raised minus 1 over alpha. And then here you have the L tilde alpha that I had somewhere. Well, I lost it now. And then the excursion looks like this. So E tau of t is just going to be whatever your process is telling you to do here, plus, and now I'm going to put here the L alpha tau minus L alpha tau minus times my profile at t, okay? And again, this I of t is going to choose the correct profile, which has got, so the trick we used was the following. So for a point, so this pi function here, what it does is looks at looks like, so you put a y here and you look at the profile which is closest, so which is the wy closest to y divided by this. Okay, so I don't think this was a perfect solution, but that's the one we got here. So basically, if you have several of these, let's say, intermediate points there, then to one of them you have an associated W1, let's say, and to one you have a certain W2, where if your orbit gets close to the point that gives you a W1, then when you take this distance, this should be closer to W1 than to W2, okay? And then we only have a problem for this when you are exactly at the same distance between W1 and W2, but the probability of hitting one of these points is 0, so it doesn't really matter for the theorem. And so it holds. Okay, and so I'm sorry, I'm already ahead of time.